Okay, so now as I said, the state of the system, which will give you the expectation value of this R operator, which gives you the polarization, now is governed by this Hamiltonian. So you have some Hamiltonian which is before the laser pulse comes in, and then there is some interaction Hamiltonian. Now I wouldn't derive how I get this interaction operator, but for a simplistic purpose, if I take a dipole and put it in an electric field, the interaction energy classically is something like P dot E, right? And that's the same kind of an interaction operator that comes in. You have Q times R, which is the polarization, P dotted with E. Right? So that's like the dipole moment dotted with the electric field vector. Now also, just to keep things simple, let's just assume that the electric field is along the Z polarized light, and that gives you just QZ times EZ. Okay. And then instead of computing the expectation value for the general R operator, you just need to compute the expectation value of the Z operator, okay, because you're generating polarization only along the Z direction. Now you can solve this for weak fields using time dependent perturbation theory. Okay. A recap of it, I am not attempting to teach this here, but for those who know it, it's a recap. For those who don't know it, it's a recipe. Okay. I know what is the solution of the system before the laser comes in. So let us say typically the gas is in its ground state. So which means this is a H naught. So I know what is the state before the laser comes in, and that is psi is an eigenstate with the ground state energy, right? It's an eigenstate of H naught. But once the field comes in, this is no more the state of the system, it evolves based on this operator. For weak fields where this perturbative series makes sense, you can treat this operator as a perturbation. So that means you can employ time dependent perturbation theory. Okay. A quick recap of time dependent perturbation theory is, let us say these psi k naughts are all the eigenstates of this H naught operator. So let us go step by step. So that means H naught acting on this state psi k naught gives you the energy times psi k naught. That's a definition of an eigenstate, right? This is an eigenstate of the H naught operator which is without the field. Now a general state can be expressed as a superposition of all these eigenstates, right? These eigenstates span the Hilbert space. So now the evolution of the state can be written with the same expansion, but each eigenstate picks up this phase factor. Correct? This is a solution of the time dependent Schrodinger equation for an eigenstate. So if I start off with some eigenstate, so let's say it is psi 1, right, and then ask the question what is the state after certain time t, it is going to be exponential minus I e k not t by h bar, right? It picks up this phase, right? That is a solution for the time dependent Schrodinger equation. Now if I have a superposition of the states, each of these eigenstates picks up such a phase, and that is a solution to this question, how does this state which is initially at time t given as this, how does this state look at a later time t? Each of these states picks up this phase factor. Okay. Now we can ask the question, how does this state look if it is not just H naught, but I have also this H prime, or which is the interaction operator. A general expansion to this is the eigenstates still span the complete space. So therefore I can have a superposition. So I can write the general state as a superposition of the eigenstates of H naught with this same time, this phase factor, but you make these coefficients time dependent. In the earlier case, let me go back to the previous slide, the time evolution had exactly the same coefficients as here. The time evolution only comes through this phase factor. But for a general case where I have H of t, the solution would have these CKs being also time dependent. Okay. Now the recipe of that, the process to get the exact solution with time dependent perturbation theory is to express Ck of t as some Ck naught plus Ck1 plus Ck2 and so on, and each of these contributions, so that is a 0th order contribution which is your original Ck. This is the first order contribution, second order contribution and so on. You can think of it like I am writing down a Taylor series, and the first term is the most important, the second one is a bit less important, the third one is even less important and so on. So therefore it is a series, and depending on your problem you can truncate it to some order. Okay. So the higher the order, the lower is the importance, okay, in terms of the actual values of these coefficients. Now, if you try to solve this, I think I need to, this equation is important. So, the general solution is given by this. So, let us examine each one. So, this CBN would means if I want to compute a coefficient of some nth order, right, then I need the coefficients at n minus 1th order. There is some phase evolution which is omega bk, and there is some matrix element vbk of t prime. So, these are the constituents of this equation. If I want coefficient of certain nth order, I need to know the coefficients of n minus 1th order. There is some e to the I omega bkt, and there is a matrix element vbk. What is this vbk? It is essentially the expectation value of psi b, the interaction operator, the laser field, at some t prime with psi k. Okay. This is such a matrix element. The time dependence comes in because the interaction operator is time dependent. Right? If you look at it, the interaction operator is something like q Ez, which is a function of time times z. Now, Ez is changing with time. You have a pulse, right? So, therefore, the electric field, the value of this electric field is changing with time. So, therefore, this matrix element would also change with time. Now, the procedure would be, so I know what is the initial state, so therefore, I know what is Ck naught, okay. So, that is my initial state, that is the superposition that is given by the coefficients of superposition. Now, if I know Ck naught, from Ck naught, I can use this integral equation and I compute Ck1, right. Cn minus 1 gives you Cn. Now, once I know Ck1, I can compute Ck2 and so on. So, you can compute it step by step and compute as many orders as you want. Now, what is this omega bk? So, let me also define this omega bk. So, this is nothing but the energy of the B state minus energy of K state divided by h bar, okay, that is this omega bk. Now, this is a general recipe to compute the state of the system with this extra operator. Okay, any questions until here? All fine? Yes. Okay, now what? Now, let us say I take this series and then I truncate it to the first order, right. I say that the wave function is psi naught plus psi 1, which means psi naught is the wave function that is constructed with Ck naught coefficients, and psi 1 is a wave function computed using Ck1 coefficients, and we are truncating all the Ck2, Ck3 and so on.
So, the psi is for a single gas molecule?
Yes, yeah, and then you do some average. It is for a single atom, whatever we are doing is for a single atom. Now, I can compute this expectation value. So, let us say I am looking at just P atomic, which is given by this expectation value of Z, or I could also take Q times Z and put them together as some, right, dipole moment mu. I want to compute this expectation value and I have two terms here. So, I can compute, when I substitute psi here, I will get total 4 terms, right. So, that means I want to compute psi mu psi, so which will give us psi naught mu psi naught, psi naught mu psi 1, and you get a complex conjugate also, and you also get psi 1 mu psi 1. Okay. Now, the polarization has these contributions. So, we classify this as the 0th order polarization, which means it has nothing to do with this correction, right. It just depends on psi naught. These two terms here are the first order correction to the polarization, because it depends on one psi naught and psi 1, and this is the second order correction to the polarization, okay, because it depends on psi 1 and psi 1. So, we can usually neglect this second order correction to polarization and restrict ourselves to the first order correction to polarization, and that is psi naught mu psi 1. Now, let us say you compute this expectation value. So, we do not do all that work, we take the formula here just for this lecture. So, let us say you compute this, what you get is the following. Let us understand this expression that you get. You have a summation over L, you start with some ground state, you have a summation over all possible states L, you have these two expectation values which is mu GL times mu LG. There is a dependence on the field strength, that is the electric field. There is something in the denominator, and overall the polarization oscillates at the driving pump frequency. All this does not have any time dependence, this is the only thing where you have the time dependence. So, your polarization is basically oscillating at the same frequency as the original driving frequency. So, therefore, you do not have any harmonics in the linear case, right. Now, let us also analyze this a little bit more. So, also you see you have this summation over all possible states, there is one particular resonance condition where this becomes large, right, and what is that resonance condition? So, I start with some ground state, I have a lot of possible excited states, and there is, if there is a resonance condition, that means this omega Lg matches with your pumping frequency, then that particular transition has a maximum contribution to the polarization. But there is also contribution from the other states, but that is usually less when you have some resonance condition that is met, that is shown in this denominator. Okay. So, for the first order correction in the polarization, the emitted frequency just oscillates at this frequency that you have already seen with a very simple analysis that we did in the first part. But if I ask the question how much will be emitted, then that is given by this prefactor, and this prefactor is what we have written as epsilon naught chi 1. So, this is a connection between the susceptibility and the more detailed microscopic description of matter. So, this is how you actually get this first order susceptibility.
How does this discretization of energy level happen?
So, that is your states for H naught. So, let us say I take any atom, then it has the ground state, you have some.
What's the atom's electron?
Yes. See, we have written an expansion, right? What was the expansion? This was an expansion in terms of the eigenstates of H naught, and H naught is a Hamiltonian of your atom. So, therefore, these are the eigenstates of the atom. Now, you have discrete states, and in general you would also have continuum states, okay? But these are the levels that we are talking about of the atom. So, this is how, this is a link between the susceptibility and the actual material response. It depends on these kind of matrix elements. Okay. You see that it is proportional to the electric field, you see that it oscillates at this pump frequency, and you have some resonance condition, and therefore, I can write this P1 to be essentially proportional to the electric field. So, this is why it is justified in this first approximation that the polarization is proportional to the electric field. Now, what if I go one more order higher? So, I do not write the wave function as just psi naught plus psi 1, but you take psi as psi naught psi 1 plus psi 2. Okay. Now, you can also compute all these kind of expectation values, and you can express P in terms of P naught, which would depend on only psi naughts. You can write down P1, which would depend on 1 psi naught plus and 1 psi 1 like last slide, and you would also have P2, which would have contributions from these three terms, right. 0 meeting 2 will give you a second order correction, 1 meeting 1 will give you a second order correction, and 2 meeting 0. Now, if 2 meets 1, that is a third order correction to polarization, and when 2 meets 2, it is a fourth order correction. So, let us examine the second order correction to polarization. Okay. So, it looks complicated formula, but let us break it apart. We will just analyze the first term, let us say. Now, what you see first is this polarization has a quadratic dependence on the field. You see that there are two E fields. Okay. So, therefore, this polarization is proportional to E square, it is depending on the intensity. You see that it oscillates at twice the frequency of the pump. Okay. And you also see that there are some matrix elements. If you look at it, it seems that I have a transition from G to M, there is a transition from M to N, and there is a transition from N to G. Okay. So these are the three transition matrix elements. So I can write this as I have a transition from some ground state to some M state. Then from some M state I have a transition to N state, and from N state I have a transition to G state, right. It looks like this. Now these M and N are not specific states, but you have a summation over all possible states, right, all possible states of H naught. So now you see why a 2 photon second order process is also usually described as a, for example, a 2 photon process, right. You would have studied in nonlinear optics problems like a second harmonic generation. What would it mean? It would absorb 2 pump photons and it would emit 1 photon which has twice the energy. And you also see these resonance conditions, right? You see something like 2 omega p and omega p, which means you have a certain resonance condition met where the difference between the energy levels has a 2 omega in one case and a omega in other case. Okay? So this is now the link. So all of this, whatever has been written in this bracket, could then be written as P2 is some E square times epsilon naught times chi 2. Now how do you get this chi 2 susceptibility? It's through computing these matrix elements. Okay. So this is the connection with the microscopic picture. Okay, any questions on this? So what's the takeaway in one line is, in the first part we just assumed polarization to be expanded in some Taylor series, but we didn't really understand fully what's the connection with the state of the atom, right. In the second part of this lecture, what we discussed is what exactly is the state of the atom. Let's see what the atom does as I put in the field. We assume that we have weak fields, therefore the state of the system can be computed using time dependent perturbation theory. We looked at the solutions, we computed the polarization, which is the expectation value of this dipole moment operator, and we exactly saw what we expect. That is, I have some quantities that depend on the state of the system, that is all these matrix elements. There is some dependence on E square, and also the temporal behavior is such that it oscillates at twice the frequency.
So the process that releases the second harmonic is the excitation after it is excited by 2 photons.
Yes. Yes. So that's the picture you can take from here. So at this model, you do not actually have photons. What you have is simply classical fields. But what you can see is that there are certain resonance conditions that are met where this particular term becomes very large, where the difference between these transition energies is such that omega and 2 omega. So therefore you say that it's a 2 photon emission, but strictly speaking there is no photon yet into this model. Okay, you have a field that oscillates at that particular frequency, just to be a little bit more rigorous. Okay, we have not invoked any quantum electrodynamical aspects.
I still didn't understand how the field, how do we output a pulse?
Yes, so that is the Maxwell's connection. So I have a source term. So when I have a source term which oscillates at twice the frequency and I solve this Maxwell's equation, automatically the electric field now becomes a superposition of the original plus this new field, right? That's a source term. So therefore now my field becomes a superposition of omega and 2 omega fields, and therefore I have in the system these 2 fields generated. Okay, that's the meaning. Okay, so how do I understand this? I say, okay, I have a dipole that is oscillating, and I analyze what are its Fourier components, and the Fourier components of this dipole will tell me what are the frequencies it is generating, and that is the analysis that we did. P1 oscillates at e to the I omega t. So therefore in the linear regime, the material is basically radiating whatever it has absorbed, it's basically re-radiating at the same frequency. So you don't see anything new.
So the field outputted by an oscillating dipole is the frequency at which the dipole is oscillating?
Yes, it's the same thing. Anything else? Yes.
Go back to the equation which, no, the last equation.
Yes.
Yeah. Here this mu is actually the dipole moment, right?
Yes.
So how does it, like now in this term you can see the numerator has mu which is for different states, or it's transition between different states?
Okay.
it's like-
So let's analyze this particular term. So it's, if I write down this, it looks like I have some psi g with the operator mu, right, psi n with mu operator psi n times psi n mu acting on psi g. So what is a physical interpretation of this, right? What is this matrix element? It gives you the probability, or essentially gives you the coefficient, whose square will give you the probability of a transition happening from the ground state to this M state. Okay, I am taking this coefficient, multiplying by another coefficient, which gives me the probability of a transition happening from M to N state, and then an N to G state. So this whole thing put together is like you are computing the probability of this sequence of transitions happening, and that's why I gave the physical interpretation to this using this level diagram.
It's like a dipole transition happening.
Yeah, here we are just assuming that the interaction is a dipole kind, so therefore it's a dipole transition.
But we also have this, like you mentioned, the dipole times mu times E is sort of giving the interaction energy also.
Yes, so we basically have made a dipole approximation. I just brushed a few things under carpet. So basically when I write this Hamiltonian, we are assuming that it's a dipole. So I have a P dot E, like it's not the most general light matter interaction operator. So the only thing I have is a dipole transition.
H naught is basically
So-
H naught is zero. There is the only the Hamiltonian we are considering, the states we are considering are all the Hamiltonian due to only the dipole. So
No, H0 is your atomic Hamiltonian, right? That's the starting point, and that's what gives you all those functions, psi naughts. Okay? On top of that, you have this perturbing field. H naught is there. It's like the kinetic energy plus the potential energy and so on.